In this question, we're given some elemental analysis data about a compound that contains carbon, hydrogen, and oxygen, and we're asked for the empirical formula of this compound. Elemental analysis data gives us the percentage by mass of each element in the compound, but empirical formula is the simplest ratio of moles. So we need a way to convert this percentage by mass to moles, and then we can find a ratio to find the empirical formula. The easiest way to do that is to assume we have 100 grams of the compound, because the percentage is the part out of 100. So if we had 100 grams of the compound, it would contain 62.4 grams of carbon, because it's 62.4%, which means 62.4 out of 100. So 100 grams gives us 62.4 grams of carbon. Similarly, it gives us 4.19 grams of hydrogen and 33.2 grams of oxygen. So if we assume we have 100 grams, we can simply change essentially the percentage sign to grams for each of the compounds, because this is the amount out of 100. Now we need to convert each of these grams into moles. So for carbon, times 1 mole of carbon on the top and 12.01 grams of carbon on the bottom, which is the molar mass of carbon on the periodic table. And when you do that, you get 5.20 moles of carbon. Since this is going to have to be an integer ratio, significant figures are not going to play a strong role, so I am going to go ahead and round to 2 decimal places or 3 total sig figs. Now, even though normally you would round at the end, here it doesn't matter because at the end we're going to get integers. I want to do the same thing for hydrogen, times 1 mole of hydrogen per 1.01 grams of hydrogen from the periodic table. And when you do that, you get 4.15 moles of hydrogen. And then finally for oxygen, times 1 mole of oxygen on top, 16.00 grams of oxygen on the bottom from the periodic table, which gives us 2.08 moles of oxygen. This gives us the moles of each of the elements in this compound. However, it is not a ratio. It's not an empirical formula yet. We next need to find a ratio. And because we want to find a whole number ratio, we want to divide by the smallest one, which in this case is 2.08. So divide them all by 2.08. In this case, it's 2.808 divided by 2.08, which equals 1. Here, we want to also divide by 2.08, and we get 1.995, which is approximately 2, because you can't have 0.995 of a hydrogen. You can have 1, you can have 2, you can have 3, but you can't have a fraction of 1, because it's a physical thing. And then finally, we're going to divide the last one by 2.08, and when you do that, you get 2.50. In the case where you get a number like 2.50, you do want to go ahead and double everything in order to get an integer. So here we want to multiply everything by 2 so that we can have all integers. In this case, the 2.50 times 2 becomes 5, 2 times 2 is 4, and 1 times 2 is 2. Now they're all integers. I should point out that in the lab, if you get a number like 2.50, your TA or whoever may tell you to round it to the nearest whole number because it's an experimental value. However, in a textbook where the numbers are going to work out well, okay, if you get a number like 0.50, you should double everything so that you get a whole number ratio. And the reason for this is you can't have half of an atom. And here we know it's not from experimental error like it might be in the lab. So we know the ratio of carbon to hydrogen to oxygen is 5 to 4 to 2. This is still not an empirical formula. So I'm going to shift this up a little bit, and the last thing we're going to do is write the empirical formula, which is C5H4O2.